Good morning, everyone. Um, so let's take a relook at the program that we have seen in the last class. So in the last class, we have seen the program to generate magic squares. So you have here the main function from line 55 to line 101. And then there is a for loop in which we are filling in the magic square. And before we enter the for loop, we initialize each and every entry of the magic square array to 0. And then there is some logic that is being followed in the for loop. And at the end, so we have a verification function which checks whether the magic square generated is in fact a magic square. If that is the case, we display that magic square. Otherwise, we print there is something wrong, something went wrong. So, couple of things here in this context. We have seen this idea of how to write our program by putting in debug macros. So for example, so we are using a macro called as debug, macro by name debug, and we will be able to compile our program. We can compile the program, this magic2.c, in three different ways. One is GCC, magic2.c. So when we compile the program using GCC magic2.c, the debug macro is not at all defined. So for example, if you see the statement, the print statement on line 66 will not be printed. And when we compile the program and run the program, similarly, the the display array function call on line 89 will not be there. So so when we compile and execute the program using this option, then what happens is, so the debug information will not be printed. No debug information will be printed on the screen. On the contrary, it is possible for us to uh, compile the program using an option such as -gcc. -d stands for define. Debug is equal to 1. And you see again magic2.c. So I am not writing that. So when we use that option, so the debug macro will be set to 1, and the statement on line 67, the printf statement on line 67 will be executed, but the display array function on line 89 will not be executed. But you use the debug if you compile the program using GCC -d debug 2, magic 2.c, then then not only since debug is equal to 2, the statement on line 67 will be executed, and the other other function called display array will also be executed. So the essential idea here is we can control during the process of building our program. We can control the amount of information that you would like to be printed on the screen by using macros such as this. And when you are printing, finally, when you are submitting your code or when you are releasing your code, you just kind of compile your code using this option, the first option. So no debug information, all these unnecessary things, they will not get into the release version of your program. I don't know what minus debug equal to 1 or 2 do. So please try it out and see what happens. I don't know. So this is a very important tool which will be used in talking about 10.5. I don't know. So you try it out and see. So it's from the semantics. Maybe debug will be replaced with no. Uh, and minus d debug 3 will execute both the macros. Of course, it will execute both the macros. Yeah, half. I think 1 by 2. It will be debug will be replaced with 1 by 2, and the 1 by 2 it gets evaluated to 0. I don't know how macro treats it, so I don't know. Yeah. So anyway, I think we are kind of getting distracted. So there's a point here, and I think there are some other things that are going in your mind. They are relevant, but you should try it out and understand how it works. That's how I will also do. So I don't know exact answer to you. So I'll just do the same and see what is going on. Okay, and then later on look at the manual or some resource and try to see what that means. Okay, whether the response that we are seeing, the behavior that we are seeing is in tune with the defined semantics of the macro processor, macro preprocessor. All right. So in production quality, yeah, I will come to that point later. So in the last time we started with some code, and later on we modified the code. This is not a variable length array, Krishna Pranit, because n is a macro here, so it's not a variable length array. Okay, it is n will be replaced with the 5. Yeah, n is defined. It's a good question though. So, anyways, so last time we start with that with some code, and we found that code is not quite neat, and so we modified the code and came up with this simple for loop which iterates for n square times. And there is some logic in this for loop, but what is important is the way we thought about this while developing this for loop. The way we thought about this for loop is by the time we reach the beginning of the for loop, the entry a of the matrix entry associated with the position c underscore row and c underscore call, it should contain an empty, it should be empty. And in our case, empty is designated with the value 0. On line 57, we are initializing it to 0. So this is the loop invariant that we would like to maintain. The rest of the code in the for loop, we have to write in such a way so that by the time we come to the beginning of the loop, this particular condition is satisfied. So when you write programs, trying to maintain these kinds of invariants, that is, when the program reaches this particular point, this particular property should be satisfied. That kind of invariance, if you can keep in your mind, then it is easy for you to argue about the correctness of the program, because this is something which many of you are asking, like no, how do I come up with an algorithm, how do I check the correctness. You need to try to, with experience, we would like to elicit such invariants such as this, so that it becomes easy for you to argue about the correctness of the program. So we can, let's say, that is the invariant that we have in mind. And so what we do is we put an assert statement at the beginning of this loop. Assert, no, this should be empty. If this is not true, then what happens is then you get into trouble. So an assertion error will be raised, and and the program terminates. So in order to use this assert statement, so we have to include this assert.h, uh, and that's what we did on line 5. So if we compile this program, as we have seen in the last class, it is going to work because there is no problem in the code. So you don't see any assertion errors. Okay. So you don't see any assertion errors. So there is a question. I will come to your question, Vivek. So in a while, and yeah. So let's say, for example, if I don't initialize this array, I forgot to initialize this array. Uh, so there is a on line 57. Earlier we are initializing the array a to 0, but now we remove the initialization statement. So now if we compile this program and when you run it, you see that there is an assertion error that is raised because when the array A is not initialized, the entries could be of garbage value. So this assertion may fail. So, and that's what happened. And when the assertion fails, you come out of the program and we exactly know on which line, in which file and on which line this assertion is has failed, and that so this will be printed. So when you are debugging large code, okay, this is a small program, but when you are debugging large code, these assertions are really useful for you to help you debug. I don't think so. When assertion fails, you come out of the program. You don't execute it. The program doesn't continue after an assertion gets failed. So let's say how does the executable know the name of the variables? C underscore call. What does you mean exe? Oh, that will be the whole thing will be stored somewhere. Good question here. So the assertion, the compiler stores the whole thing somewhere. Very good question, actually. Uh, no, even without using -g also, it will still work. So what is an assertion? An assertion, just there's a question on explaining the assertion again. So Mihir has a very good question. So I didn't think about it before actually. So number one, what will an assertion do? It will check the condition that is given as here. And if that condition is true, then assertion is null, nothing happens. But if the condition is false, the program stops execution, and the assertion error, the line on which the assertion failed, will be printed on the screen. This is what we are seeing. See, the assertion failed on line 70 of magic2.c. The assertion failed and it got printed. Uh, so just a quick thing. So when the whole thing, no, like this whole C program gets generated into assembly code, how is it at the runtime this assertion string is getting printed? So the compiler will kind of store this whole thing in the form of a string somewhere in the memory, and it prints when this assertion fails, print this string. And it is not so much valuable for, there are two things that I would like to say. Only those strings which are there in the assert, you will be able to see, but not others. Uh, Assertion, it is at a runtime thing, it is not a compilation thing. Okay. Uh, no, assertion is not done at the time of compilation. How can, without running this program, you know whether a particular row or a column entry in the matrix is true? Well, so I don't want to get into the details how the assertion prints this thing. It's a good question. But I know how it does, but let's not. It requires a bit of digression to exactly explain how assertion is able to print this whole thing when the assertion gets failed. All right. So, but one thing that I want you to get clarified, assertion is not a compile time thing. If you look at debug, whether this printf statement will be included in the program or not, it is decided at the compile time based on whether this debug macro is greater than or equal to 1. But the actual printf anyway happens when you execute the program. Similarly, assertion, it is not a compile time thing. It is a runtime thing. When you run the program, you will get to know whether that assertion is passed or not. So right now, assertion is not in the debug mode. I will just take a moment and tell what is going to happen. So yeah, let's make it. So now what we can do is, in order to disable assertions, okay, so like for example, there is a macro called as ndebug. If you define it, then assertions will be disabled. So gcc so now what happens is assertion got disabled because we have defined this macro ndebug. So it seems when we define this macro ndebug, then all assertions will be automatically be disabled. So an alternate way of no, if you want instead, you can also say minus d n debug. So that is, you are compiling your program with this definition, then that means disable assertions. And if you remove this, then what happens is assertions will work. For me, a better a cleaner way is we can use another macro called as assert in order to enable or disable the assert condition. So let me tell you another way, at least for this class, in order to make it easy on you. Let's see this. Okay, hash if def assert. So those of you who are bit lost in with respect to ndebug, just leave that aside. Okay. So similar to debug macro, we can define a assert macro also. Like for example, when we are debugging our program, we can use something like gcc d debug is equal to 1 minus d assert magic 2 dots. And then when we run the program, so like this is getting printed because the debug macro is enabled and it is at level 1. And this is and the assertion is enabled because we are using this flag to compile the program. And if we don't use these two, then what happens is so this is what happens. So there is no debug information printed, assertions are not verified, and so that's it. What do you mean by it worked before? No, the program right now, there is a problem because I removed the initialization. I don't know how many of you are paying attention, or maybe you may have missed it in all the verbiage. So right now the program is not supposed to work right because on line 57, I removed initialization for array A. So because of that, this assertion is getting failed. When we kind of disable this assertion, what happens is the program goes wrong. And finally, when we come out of this for loop, And when we try to do this verify magic comparison, when we check whether the generated magic square is a valid magic square or not, it turns out it is not a valid magic square. So something went wrong, message will be printed. So one thing, so in the last class, we were having this discussion. What is the advantage of, no, like, this is one way of defining the debug and assert macros. Another way of defining the macros is like, for example, I can say hash define assert. That is, we go and change the source code, hash define debug. So this is another way of doing it. So this is one way of doing it, or this is another way of doing it. So one way of doing it is using the command line, and another way of doing it is by going to the source code and putting these macros. There is no necessity for using the macros in caps, but it makes it easier for us to understand that they are macros. That's a convention we follow. So now I have a question for you. Between these two options, that is, one option is to define these macros within the program versus another option is to define these macros using the compiler option. Which of these two options are preferable? Which of these two options are preferable? So why is that? I am seeing mostly everyone is saying, so someone said defining them in the source code. So why is it defining on the terminal is a good option? Hash define might become confusing. We don't have to open the source code every time. Yes, so for this small program, uh, and memory is not a big deal, Anusha. But primary thing is uh, when you are working on compiler, let's say if you look at GCC, when you I don't want to confuse you with GCC compiler. Let's say you are compiling a big software which has some 20,000 files in it. If there is a software which has 20,000 files in it, and no, with all the debugs, so you want to go and change these 20,000 files, no, make hash define debug is equal to 1, hash define debug is equal to 1, each of the files. It's not possible, right? Does it make sense for you? And that is the case. That is a very practical scenario where when you build software, real software, it's easy to have some 1,000 files, 10,000 files, 20,000 files. It's very easy to have. And it's not possible for you to go and look into each of these files and modify the hash define. It's not possible. So the easiest option is to use it on the compiler side as a compiler option. That's the easiest option. Are you with me here? The second thing, no, like so usually when we work with the program, you use the debug and assert options and you debug your program. And after that, once you are done, uh, you just compile it using magic2.c and you are done. So you don't use those options. Now the asserts and no debug information, all that is no longer printed. So I'm so surprised actually. I should share one interesting experience I have recently. So like just like GCC is a compiler, so there is another compiler called as Clang compiler. I was trying to compile the Clang compiler. So you just know Clang compiler is also written in C++. You compile that compiler using no, GCC. So it is possible it is possible to compile Clang in three modes. Uh, so one is in a release mode. Release it's you can this is what is called as release mode, and then you can kind of compile it in debug mode, and you can compile it in debug plus assertions mode, and then so this is one option, this is second option, this is third option, this is the fourth option is assertions. So the size of the software is so big um, that when you compile the program, LLVM compiler or the Clang compiler in the debug mode, the amount of disk memory that is required is like something like 150 GB or something like that. I didn't realize, and what I did is I just compiled the program, and my whole file system has become full. And what happened is I'm not able to reboot my system because my file system has become full. Then I have to boot using a different option, and then remove that installation, and so uh, lots of problems. So so what the ideal thing for, so those of you, so let's say the suggested thing for people is, if you are modifying the Clang compiler, then you compile it in the assertions mode. So release mode is the case where it is supplied to us. So all the debug information, assertions, nothing will be there. Pure software which does stuff for you will be there. So those people who are building that Clang compiler, they want to compile it in the debug mode or the assertions mode in order to see that if there is something wrong in a particular feature that they are implementing in the compiler, if it is working or not. Yeah, 3 and 2, these are pretty bad. So both 3 and 2 are pretty bad. So when you are in a development mode, like for example, for Clang compiler, the suggested is compile it using assertions mode so that you get some kind of information. I think in the good question. So my best guess is in the debug mode, lots of information about the variables, the whole symbol table. No, in a program there will be thousands and of variables that are there, and lots of stuff is there. I think all of that is dumped. I think so. But whereas in the assertions mode, all that information will not be stored, only assertions will be enabled, and only possible extra storage that is required is the string that we pass it to, to the assertion statement. It could be stored somewhere because when the assertion fails, you want to print that assertion on the screen. So that's the reason. Yeah, minus G. When we say debug mode, so it's not minus G. Uh, uh, Is it possible to compile a partial file line by line? Not really, Frame. You can, if your program is present in 30,000 files, you can compile one file, leaving out the rest of the files. So, okay. So anyway, I would like to uh, stop the discussion on this debug and assertions here. The primary thing I want you to remember is this statement, okay? That is, it is possible to control the debug behavior of your program by defining the macros appropriately. You can do it either at the command line, or you can do it uh, or you can or you can do it within the file. So And there are a couple of questions, and this is the main thing. There are a couple of questions um which I thought are important, but I forgot. Something like, is debug and assert, are they keywords? Something like that. Let me check that those questions. Someone asked it. I don't know what that. Anyway, if you may want to ask it again. Yeah, yeah. So no, ndebug is not a keyword. Okay, it's not a keyword, or a, because it doesn't. It is something. Uh, it's a predefined macro. It's a predefined macro. It's all user defined. Ndebug is user defined. That's the right way to put it. So Shashwat, it is not, ndebug is not a reserved identifier or anything like that. No. So there are nothing like reserved identifiers actually to start with. That's true. The combination of frames and Kishores is the right thing to see. That is, number one, it is user defined, and number two, the assert library is set up to take into consideration whether that ndebug macro is defined or not. Okay, so if you put two statements made, one statement from frame and one statement by Kishore, so together they answer the complete. Okay, like for example, what it means is, like for example, if you do something like if assert x is not equal to 0, then what happens is, if you go and look in the code, it seems assert is actually a macro, and it is something like if def n debug or something like that. Then you want to check if x is not equal to 0, don't do anything else, print something and exit, something like that. Okay, so this is how the whole assert statement could have been implemented in the assert.h file. So my question for you, for all of you who are more inquisitive, is go look into the file assert.h and check how this assert is defined. How this assert is defined. This is a homework. No, we can redefine ndebug. That's what we are doing, right? So we can. It's possible for us to redefine ndebug. It's not in the assert file. You can go change the assert file, no, but you need to have root permissions, and you are going to change the way the standard semantics of assert. You are going to change if you redefine it in the assert file. The question for you is, I want you to go see in the assert.h file. In the assert.h file, it could be present somewhere in some include directory. So number one, find where assert.h is located, okay, in your system. This is a very good homework to do. Number two, so check the definition of assert, and I want you to know, is it a definition or a declaration? And the third question is it a macro or a function? Is it a macro or a function call? These are the three questions. These are the three questions I would like you to check. Are you all with me here? Okay. Good. I'm thinking these 1 hour classes are not sufficient. So there's lots of things I wanted to discuss today. Uh, let's have two options. I'm just thinking. Hmm, uh, okay, let's see. Let's see. So there is one idea I wanted to discuss. Maybe I will take it up in the next class. But instead, I want to do something which helps you in doing your homework. Okay, let's go to your homework. So now we are moving to one interesting, we are moving on. I know you have some questions on assert. We can take those questions later. But the core ideas I have, I hope all of you understood the core ideas and we should move on. So the first important idea here, so let me reposition my, yes, I will solve some problems using recursion for sure, definitely. Great. So we know that the memory, our main memory view is this. Our main memory is a linear array of bytes. This is the first view that we have. So this is byte 0, this is byte 1, this is byte 2, so on and so forth. And then every byte, it's a sequence of 8 bits. So 1, 2, 3, 4, 5. Yeah, maybe I'll put one. So it's every byte, it's a sequence of 8 bits. So when you store uh, a character will be stored in using 1 byte. And let's say uh, an integer is allocated 4 bytes. So let's say if there is an integer, so let's say an integer, if you think of an integer, so an integer will have 4 bytes. Let's call them as this is B0, B1, B2, B3. An integer is a sequence of 4 bytes or 32 bits. 32 bits, 4 bytes. So what happens is when we store an integer in the memory, uh, so every memory location, every addressable memory location, it can hold only 1 byte. So what happens is, like for example, if the address of some variable starts at 5, then what happens is B0 will be stored here, B1 will be stored here, B2 will be stored here, B3 will be stored here. So these 32 bits or 4 bytes are stored in consecutive the 4 bytes. So here an important observation is the a byte is the smallest addressable entity in our computing system. A byte is the smallest addressable entity in our computing system. So let's say if you want to access, let's say this particular bit, okay, you want to access this particular bit. This particular bit is, like this is B0, B1, B2, B3. You want to access bit B3 of byte B0 of byte which is present at address 0, then there is no direct way of doing it. So you have to read the whole byte, and then we internally we will figure out a way of manipulating this bit. Either read that bit, make that bit equal to 1 or make it equal to 0. So we do it using some other mechanism. because there is no address for a bit within a byte. Similarly, if you want to access, let's say, this particular bit, let's say this is bit B2 of byte 2, then you cannot go directly go ahead and access bit B2 of byte 2. You have to access the whole of this byte, and then you need to find a way to access this particular bit. Okay, this is the first idea. Are you all with me here on this particular idea? All right. Uh, Yeah, that is minimum 1 byte. So read or write is minimum 1 byte. Yeah. So there are what are called as, just like we can do addition multiplication of two integers. There is what is also called as bitwise arithmetic. Okay, so bitwise operators or arithmetic. In order to understand these bitwise operators and bitwise arithmetic, let's look at a few functions which work on bits. So let's say there are two bits, let's say bit A and B. And so there are the bit A can be equal to 0, bit B can be equal to 0. So if you see, there are four possible things for this. And we can define a function, and which, for example, the first function we can kind of define between them is what is called as an AND function. What is an AND function? The AND function, it will be equal to 0 if so this is AND is nothing but so AND, the two parameters to this AND function are uh, these two bits. If both A and if either A or B is equal to 0, then AND will be equal to 0. So this is 0, this is 0, this is 0, this is 1. This is what is called as an AND function. You will study more about this and other things in a course on digital logic. Yeah, so but for this class, this discussion suffices. Similarly, we can have an OR function. So A, B. So why not? I'll just extend this table here. So we can have an OR of A comma B. So OR function. So if either A or B is equal to 1, then it becomes 1. So in the first case where both of them are equal to 0, it is 0. In the second case, 1. Third case, 1, 1. So this is the OR function. And then there is a one more function called as exclusive OR of A comma B. So exclusive OR, what it does is, if both of them are equal to 0, or if both the bits are the same, the output will be 0. If the bits are different, then they will be 1. So like for example, in the first case, 0, 0, it is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is 0. This is how the exclusive OR is. I didn't get Krishna Pranit's comment. I used and or in some quotes. Huh? I don't know. Oh, okay. Not in ICT. Yeah? Okay, okay. Good then. So I don't need to spend much time here. So we can lift this logic on which kind of so we can lift this logic and apply it on what do I say, at a byte level. Like for example, let's say 1 byte is 100 0100, another is 0100 0110. So this is one byte, this is another byte. And when we take the AND of these two, when we take the AND of these two, then what do we get? When we take the AND of these two, so we take this bit and this bit, and we take an and we take this bit and this bit, we take an AND, so on and so forth. So this is called as the bitwise operator because we just take this byte, but then the application of that logic is on a per bit basis. So when you take the AND of these two, you get 0. When you take the AND of these two, you get 0. And then 3 more zeros, 1. So this one corresponds to this, and then 0, 0. All right. So in C, the and the operators that we use for and is this, and for or it is this, and then for exclusive or I forgot, maybe it is this exclusive or. And then there is one important function that is not. So let's say if it is equal to 0, 1, so the not function is you flip the bit. This is not our complement function. So if you take the complement, and the symbol and the operator for complement in C is this. So when you apply a complement, so for example, on this particular thing, if you apply a complement, then what happens is wherever 0 is present, it becomes 1. So the first 5 zeros gets translated into first 5s, and then 0, 1, 1. This is what happens. There are two more things that we need to know. One is called as a shift operators. Okay, so we have seen about the shift operators before, but let's revisit them. Okay, so let's say you have a byte. Uh, let's say there is a variable x. Let's say it is a byte, and the data that is present in that variable x, it is something like 0, 1, 0, 0, 1, 0, 1, 0. So we can apply a shift operator like x less than, this is what is called as a left shift operator. When we say x less than 2, then that means take this whole thing and shift it to the left by 2 bits. So when you shift it to the left by 2 bits, these 2 bits, the green colored bits, these 2 green colored bits, they will fall off, and these bits, they will shift to the left, and the least significant 2 bits which are there, they will be filled up with zeros. So that's what happens. So after we do this, so this the value that will be present, so the value that will be present is 0, 0, 1, 0, 1, 0, 0, 0. So these 2 bits fall off, and in the least significant 2 bits, you get 2 zeros. This is what happens. Is it possible to shift and fill the new space with ones? No, it is not possible. So there is one more thing, that is the right shift. Right shift is a very tricky thing. I will yeah, so I will hold a discussion on right shift. There are two kinds of right shifts, and that becomes a bit tricky. So x greater than 2. So there are two ways of doing right shift. So when we do right shift, what happens is these two least significant 2 bits, they will fall off. So what we get is, for example, 0, 0, 1, 0, 1, 0. And then we would like a couple of bits. We want, these are the, yeah, so these 5 bit, these 6 bits are there. And so there are two ways of filling this up. So one way of doing it is you fill them with 0, and so there is, depending upon the most significant bit, something weird happens. So for the time being, I would like to keep the right shift like that. And also when you are doing right shift, just for the time being, what I would like you to think is, whenever you are doing right shift, this better be an unsigned integer. Just keep this hint, and then we will revisit why this should be the case. Okay, in the homework problems, etc., when you are working, when at any place where you have to do right shift, uh, so define that variable as an unsigned integer. Otherwise, some weird things can happen. Are you with me here? For the time being, just take this hit. I will give a very detailed answer why this is, yeah, all this 2's complement stuff and other things comes into picture and make our life bit messier. So for the time being, you declare it as an unsigned integer and we'll deal with it later. Yeah, the negative numbers, the most significant bit is equal to 1. And when we do a shift, there are two kinds of shift, logical shift and arithmetic shift. And so we'll look into it later. Okay, are you all with me here till this point? Are you with me on the shift operations? Is there anyone who has a problem? Can you say, send me a private message if you're not sure about so this is a constant thing. So when you are not sure about putting your questions or expressing your doubts, you can on the public forum send a private message to me. The right shift part. Okay. So let's do one thing. The symbols for exclusive or etc. we will see later. Okay. Uh, let's do one thing. Let's go to the next page. So if you take a yeah, so let's take a 4 byte integer. This is our 4 byte integer. So since it's 4 bytes, so it's 32 bits. So let's call the bit starting at the leftmost point, rightmost point as the least significant bit, and this bit as the next bit, so on and so forth. Right? So when you take this one and when you shift it to the left by, let's say, 2 bits, then how will this look like? Whether this 4 bytes, it can be a signed integer or unsigned integer, it doesn't matter. When you shift it to the left by 2 bits, what you will get is B31 falls off. B31 falls off and B30 also falls off. B31 falls off, B30 falls off, but B29 remains. B28 remains, so on and so forth. And so here you will have B1, you will have B0, and then you have 2 bits, 0 and 0. Are you with me on this one? We'll take one thing at a time. Are you with me on this particular thing? Great. And the question is usually when we have these things, so we call no the bits on the rightmost side as least significant bits. Least significant bits. I used it without defining. I should actually apologize. And the bits which are towards the left side, we call them as most significant bits. Why most significant? When in terms of value, they can possibly contribute more value. So MSB. So now you take this same thing and instead of applying, like, so you want to shift it to the right by 2 bits, greater than greater than 2. So when we want to shift it by right by 2 bits, we have to consider two cases. One is the number that we are, the variable that we are shifting, it is an unsigned integer or it is a signed integer. These are the two cases we need to consider. If it is an unsigned integer, what happens is when we shift it to the right by 2 bits, so B1 and B0, they will fall off. Okay, so actually whether it is an unsigned integer or a signed integer, the bits B1 and 0, they will fall off. Not a problem. So B1 and 0 will fall off, B2 will be here, B3 will be here, and B31 will be here and B30 will be here, so on and so forth. Bits B0 and B1, they will fall off. But in the case of if it's an unsigned integer, these bits will be filled with zeros, 0, 0. Does it make sense? Are you all with me here so far? It's very simple, na? So you want to, you are shifting this number to the right, whether the look at the type of the variable, if it's a signed integer or an unsigned integer. If it's an unsigned integer, the shift operation is very simple. The least significant 2 bits B1 and 0 will fall off, and the space will be created in the most significant 2 bits, and you fill them with zeros. Are you with me? So Pratyaksh, you said they have an issue here. Is it clear? But now let's say it is, in the case of signed also, the story is the same. But the only thing is, what do you fill here? What do you fill here? That's a very important question. Okay. So here, filling this here, there are two cases. Filling this here, there are two cases. The first case is B31 is equal to 1, and the second, let's call it as B31 is equal to 1 and B31 is equal to 0. Later on, when we study about representation of variables in more detail, you will understand for negative numbers, the most significant bit will be 1, and for positive numbers, the most significant bit is equal to 0. Oh, you did this in ICT too? So awesome then. Oh, so then why am I explaining all this stuff? We will have a very technical discussion on this later, but but anyway, so if it is B31, if it is equal to 1, that is the number is equal to, is a negative number, then what happens is the most significant 2 bits, it will be equal to, it will be filled with ones, and we get this. This particular thing is what is called as this particular approach, where if it's a signed number, and then here, uh, this will be 0, 0, B31, B2. Or if you want to put it in a very generalized fashion, so the generalized fashion is, B31, 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 B30, so on up to B2. So if B31 is equal to 1, these two bits will be equal to 1. If B31 is equal to 0, these bits will be equal to 0. So Lakshman, so we will exactly see why we do it, not in this class, in a few classes later. So before I answer Shashwat's question, I will, in order to answer Shashwat's question, also I'll answer Shashwat's question not in this class, So you are right, Shashwat, your observation is right. No, if you sometimes when you left shift a positive number, it can become a negative number. It is possible. By looking at the sign bit, we can say if it's a signed number or unsigned number. Okay. So what I want you to do is, no, we can say, no, that we cannot. I mean, by looking at any bits, a bit can mean, okay, guys, I think let's take a step back. Okay. Uh, Hold on to your questions for a moment. Number one, do you understand this, how the semantics of the shift operation? That's the first question I want to have. The semantics of the shift operation, are you all with me? That's the only question I want. Uh, so now if you understand the semantics of the shift question, we will take a pause here in in this line of thinking, because we will have at least one or two classes where we get into clear details, and I will explain what happens under the hood. What is two's complement representation, why it is important, and so all interesting stuff I will tell you, and what are the how things can go wrong for you, overflow conditions, lots of other things I will tell you in one of the later classes. But for the time being, I am discussing this shift operation because it is necessary for you to perform one particular assignment on encryption in uh, encryption in lab 5. That's the reason why I'm talking about shift operation. Without that, you will not be able to do it. And when we are doing that, you don't care about this particular path, this whole thing, no? This whole path, this whole tree side, you don't care. You work here itself. You work here when you are doing in lab 5 part 3, when there is one problem on encryption. Yeah, that's true. So this is the thing that you will be working with. This is the branch you will be working with. So this part we will revisit it later, but I want you to understand this part. So I want to facilitate so that we can do lab 5 part 3. Are you happy? There is a difference between left and right shifts, Lakshmanan. So exactly. So so filling the LSB is not going to change with 1 or 0 is not going to change the value of or the sign of a number. That's true. MSB holds the sign bit. That's true. That's true. Shashwat's question is valid and it will happen. I'll answer that. Right now, I don't want you to think about all those things. I just want you to understand how the shift operator behaves. Nothing more than that. Because there is no easy answer to all of them. So I want all of you who are kind of, you have valid questions which I don't want to answer now, but few classes later I will take them up and give a detailed answer. But I would like you to understand how the left shift and right shift operators work on unsigned integers, the syntax and semantics. If you are all with me on this, I will proceed to the next idea. Shall I go ahead? Also, I want to do a time check. So is it all right if I take, let's say, 10-15 minutes more? Okay. So because I want to clear up this thing. So now let's, yeah. So now let's go to the code. Let's go to, so what I would like to do right now is write code. This is magic 2. This is done. So let's come to bits.c. Okay, so what we want to do is, the first thing that we would like to do is, we want to read an integer and we want to print the bit pattern of the integer. So here on line number 27, we are reading an integer. So, and we want to call this function print bits n. So this will pass this integer to it, and on line 20, we will print this integer. And we want to define a function uh, read bit where we pass the integer and we tell the position of the bit that we would like to read. So let's say if that function is available, so then what do we do? So what we do is we say, yeah, so printf. Um, So let's see how it works. Bit representation of, or let me actually make it simpler, %d underscore 2. Underscore means subscript 2. Uh, this is what so now what we would like to do is we want to read the bits of n from least significant bit to the most significant bit. Actually, I am not exactly sure about the size of the integer. I think it is 4 bytes. So instead I use this size of, I think it's a macro. I think it is 4. So plus I, and so read bit I. So we are printing it from the least significant bit to the most significant bit. Oh, size of int. Okay. Does this work? Thank you. And then how do we do this read bit business? So in order to, so this is where I would like you to pay attention, the logic for read bit. So let's focus just on 8 bits for the sake of simplicity. So B0 to B7. So in order to read this bit, what we would like to do is we want to AND, let's say you want to read bit BI. So you want to AND this thing with another thing where everything is 0 except this bit position is equal to 1. Okay, someone is not happy here. Are you with me on here on this logic? So if what happens is when we AND this B0 to B2, so what happens is wherever the 0 here is present, independent of what bit it is, it gets 0. This will be 0, this will be 0, this will be 0, this will be 0. And what the only thing that changes is when you AND 1 with BI, if BI is equal to 0, the result will be equal to 0. If BI is equal to 1, the result will be equal to 1. So this is what we get. So if bit bi is equal to 0, this whole value, now if you think about it, if bi is equal to 0, if bi is equal to 0, uh, so this bi is equal to 0, the value of this whole integer is equal to 0. And if bi is not equal to 0, the value of this whole thing is something which is not equal to 0, some value. And that value, I think it should be 2 power. So the simple idea here is what we do is so we do a return on you want to take n and you want to AND it with 1 less than pos, and yeah, so you left shift it to by that, and then you check. Does this statement make sense? Line number 6. So what are we doing? Let's say, uh, uh, so here what we are doing is we start with n. So let's say you are trying to read position 0. So let's look at, so what is the function? So there are different values for pos, 0, 1, 2, 3, and so 1 less than pos. So 1 less than, that is you shift 1 by 0 bits, the 1 remains as it is. And you shift 1 by 1 bit, then what we get is 1 0. So when we say it is 1, this is all zeros followed by 1. This is all zeros followed by 1 0. And when you do this shift, this is all zeros followed by 1 0 0. And this is all zeros followed by 1 0 0 0. Argue with me on this one, this particular. Okay, so let's do this. Let me clear this up again. So just take a look at this thing. Okay, so you want to, let's draw an expression tree. So you want to AND n with this is the expression tree. So what happens? So if pos is equal to I, what will be the resulting bit pattern that you get? If pos is equal to I, when you apply left shift on this, then you get this bit will be the 0th bit is equal to 0. This bit is equal to 0. This is bit B0. This is bit 1. This is bit 2. So somewhere bit BI, so that will be equal to 1. And everything else will be equal to zeros. Okay. Are you with me on this operation? What will happen if you take 1 and shift it to the left by pos? See, there are different approaches, guys. Okay, I'm just taking one approach. I just want you to follow. Those of you who are able to get other approaches, it's all right. Those of you who are not able to see it, can you try to understand the logic that we have? So essentially what we are doing is, so from here, this is what we are trying to do. So this is n. These are all different bits of n. Let's say, uh, our interest is on this green bit. Let's say our interest is on green bit. So in order to, we want to extract this green bit. This green bit is bi, and this is given by pos. And then what we are doing is we want to take this one and AND it with another number. And the way we would like to AND it is like this. Wherever this green bit is present, this is the new number. There 1 should be present, and in the rest of the places 0 should be present. Are you with me here? So now when you take the AND of n, this is nothing but 1 less than, sorry, and this is nothing but, let me use this color. So 1 less than pos. So now when you take the AND of these things, all these bits will become equal to 0. The only thing that no, this particular bit, this will be, the result will be equal to bi. That is, if bi is equal to 0, no, this bit will be the result, no, the resultant bit, it will be equal to 0. If bi is equal to 1, it is equal to. So if bi is equal to 0, then what happens is this whole value becomes equal to 0, in which case we should be returning 0. Or we return 1. How many of you are with me here on this one? How did we convert n? We don't convert n into binary. Scan of n, everything will be stored in the form of binary. So when scanf, no, how do you think, how will you think n is stored in computer? So there is no representation for 22, 3. Let's say if n is equal to 23, there is no hardware representation for 2 and 3 in a non-binary form. So you convert 23 into a binary form, and then uh, no, if this whole thing is equal to 0, what will, if this whole thing is equal to 0, then yeah, so then we should return 0, right? Because the bit bi is equal to 0. Oh, 0 means false. Okay, sorry. Okay, so if it is, yeah, if the whole thing is 0, then yeah, if the whole thing is some non-zero number, good, yeah. Is there anyone who is kind of lost here? Can you send me a message privately if you want me to repeat one more time? Okay, so clear. Okay. Let me rewrite the code actually. Uh, So let me define something called as mask. And so I have a variable called as mask, and so in the variable mask, I store one less than pause. And also, in order to make my life simple, I will just make it as unsigned int. Okay. So so what is the value on line? So after on line 7, if you see on line 7, what do you have here? When you take one and uh, so when you yeah, I will run the code, and what I would like you to do is, so this is what uh, I want you to understand here. So this is pause. Let's look at this table. There are three ways of looking at this table. If pause is equal to 0 and 1 less than pause, uh, so this is also 1 less than pause, but in a different form. If it is 1 less than pause, you shift 1 by 0 bits. If you shift 1 by 0 bits, you don't get anything. So 1 will remain as it is. And the value, if you think of it in terms of value, its value is 2 power 0. Are you with me here on this first line? Let's take one step at a time, guys. Okay. So let's fix this one. Now let's say if pause is equal to 1, then so this will be all zeros followed by 1 0, and its value is 2 power 1. Are you good here on the second line also? So similarly, if you keep going, if pause is equal to I, then what happens is, so you will see a sequence of zeros, 1 followed by a sequence of zeros. And where is this I, where is this 1 present? So this 1 is present. So you have shifted 1 by, so this is equal to I zeros. So and the value is 2 power I. Does this make sense? What happens on row I? You're all with me here, right? So now, so you take this one, so you take this whole, so let's say you want to read bit I. So remember, this is bit B0, bit 1, bit 2, and this is bit I. So when we want to read bit I, we want to create a bit pattern where the ith bit is equal to 1 and the rest are all equal to 0. Okay, so where the ith bit is equal to 1. So here, so this bit Bi is equal to 1 and the rest are all equal to 0. And this is what we are doing here on line 7. Mask is equal to this. I hope you're all with me till this particular point. So now what we do is we take this mask, and we AND it with n. Okay, so let's say there's a temporary variable. We take n and we AND it with the mask. I'm using a temporary variable temp, and so we take the temporary variable, we are storing the mask. Okay, so when we do this masking business, okay, so this is n and you have a temp here, and when you do AND of this with AND of this, what happens is, if you look at temp, all the bits will be equal to 0. Let's use a green. So this is the green bit. Bi is the green bit. Okay. So here, so n can have any bits here. We don't have any concern. But if you take a 0 here and when you AND it, what happens? This becomes a 0. So if you see, all these things become 0. And similarly, this is all becomes equal to 0. How do Kishore has Kush has this question, how will you have this? Because one is represented internally as 0 0 0 0 1. So if you shift it to the left by one one position, then this is all equal to 1 0. No? So one is represented as in the bits, it is represented as all zeros followed by 1. Does it make sense, Kush? Okay. So what is this step? Are you all with me on this particular step? You take 0 and AND it with this bit of uh, the single AND is bitwise AND. This is not a logical AND. I want to make a distinction that there is something called as this is a logical AND which we use for conditional statements. That is different from the single AND. Similarly, uh, yeah, so all right. So now similar, if you see wherever 0 is present here, independent of what the corresponding n bit is, it gets zeroed out. But the only thing that matters is this. Okay, if you see here bit bi, so here this is bit bi. So when you AND 1 with bi, so when you AND 1 with bi, what do you get? You get bi, because if bi is equal to 0, 1 ANDed with bi is equal to 0. If bi is equal to 0, sorry, 1, then 1 ANDed with 1 is 1. So what we get is here b. Are you with me till statement uh, on line 9? No, no, please take one step at a time. Are you all with me on how what temp contains? Yeah, so now what can we say if bit bi is equal to 0, what is the value of temp? If bit bi is equal to 0, what is the value of temp? So there are two cases. If temp is equal to 0, what should we return if temp is equal to 0? If temp is equal to 0, then we should return 0. If temp is not equal to 0, it can be any value. In fact, it will be 2 power I. If bi is equal to 1, then we return 1. Does this make sense? Are you all with me here? 100%? All happy? Are we good? Shall we go ahead? Is there anyone who still has a problem? You can send me a message privately if you're okay. So I am going to clear this thing and we will run the program. And here what we are doing is we are printing it from I is equal to 0. So I think someone asked this question. We are printing it in the opposite direction. So what should we do? Yeah. So we should start from so now we are starting with MSB and we are going to LSB. So so shall we run the program and see what happens now? Let's see. Let's enter 1. See, how is 1 represented? Someone asked the question, how is 1 represented? 1 is represented as all zeros followed by 1. How is 0 represented? It is all zeros. How is 2 represented? 2 power 1. How is 4 represented? Like this. How is 5 represented? Like this. Does the program make sense? And let's say if you want to know how is minus 1 is represented like this. So this is a representation for minus 1 in 2's complement form. If you take any number, some arbitrary number, if you go look at the most significant bit, this bit will be equal to 1. That is a sign bit. Are you all with me here till this point? Then I will show you 2 more things and then we can take a break for today. I don't know why it all once came. Huh. Oh, that is int max. Okay. So, okay, I don't want to get into those int max issues. We will take them up in a different class. I want to finish couple of more ideas. That is, let's say, because these ideas are important for you, if you know these ideas, then you will be able to do the homework maybe a bit better. Okay. So one is reading the bit. The other is if you want to set a bit. How can you tell me the logic for setting a bit? Or maybe I will do this thing for you. The homework for you today is I will release this code and I want you to write code for setting a bit and masking a bit. What is setting a bit? So let's say that's a good homework. Maybe you can submit it by today. So this is what I would like you to do. Let's say this is the set bit function. What it will take is it will take n, the integer n, and the ith bit here given by pos, it will set it to equal to 1. It could be 0 before it or 1. Independent of that, it should be made equal to 1. And the mask bit, what it will do is it will make it equal to 0. So set means set to 1, mask means make it equal to 0, the corresponding bit equal to 0. So if you do this thing, it will be a good thought exercise for you to work. Yeah, that's true. No shifting, nothing, guys. There is only go to that particular position, make that bit equal to 1. Okay. Thank you. Happy? So set bit and clear bit, it makes okay. So good. So I will upload this code. I want you to work on these 2 functions. And so I think that's all I have for today. Let's not go any further because your brain would be full.